So I'm going to talk today about how can high-performance computing help design more efficient jet engines. And we can essentially distinguish between two different parts. One is they can provide physical insight, and they can also help us with machine learning approaches. And I'll discuss these in more detail. But first of all, why do we actually need better jet engines? Today's jet engines are already a marvel of engineering. They are much better than the first generation of engines. So if we just look at this difference here between the Boeing 707 engines that we had about 50 years ago and a new engine that we have on a Qantas Dreamliner, the efficiency has gone from about 20% that we had on the first jets to more than 40% on the latest generation of engines. We had about 30% on the 747, the queen of the skies that's been retired just last year. Also, these engines have become a lot quieter. So we've reduced noise by about 30 dB. And that's really a reduction of more than 80% of the noise that we had in the early generation of engines. And engines have become a lot cleaner as well. So we've seen a reduction of more than 50% reduction in emissions. For example, things like NOx. These engines also are much more reliable. So we can now fly across the Pacific using just two engines. In the olden days, we needed at least four engines, or we needed four engines. And the service intervals have become a lot longer, which ultimately saves passenger money. So why do we need better engines? Well, aviation is still predicted to grow further despite the dip that we're seeing at the moment due to the pandemic, but the long-term projections still say that we will see aviation grow. And we need the next generation of engines to do this sustainably with less impact on the environment. And just put it into context, commercial aviation burns about 350 billion liters of fuel. And I think it's around 9 billion liters of fuel in Australia alone. So for each percent that a jet engine can be made more efficient, we can reduce the fuel cost by billions of dollars, or just in the Australian context, by roughly $60 million. And also we can save, or we can reduce the emissions by a good fraction. So there's definitely a need to keep designing better engines and also engines that ultimately can use newer fuels, sustainably generated fuels that basically don't produce CO2. So how can high performance computing help? Well, these engines that we have today are really complex machines that have many parts. And they take a long time to develop, up to a decade in many cases, and that costs billions of dollars. So that's because building prototypes of these very complex systems and machines is very expensive and it's time consuming. And if you want to try out different things, you really can't afford to try too many things if every time you have to build a new prototype. It's also difficult to measure the airflow inside of a jet engine. So you can imagine a lot of these parts are spinning at very high velocities. We also see very high temperatures and we see very high pressures. So instrumenting all of this and getting all this information that we actually need to build a better machine is very difficult. So this is where we hope that computational models can be of help, as potentially they can fast track designs. And they can allow designers to take virtual risks, or try new things. And if they don't work, it doesn't matter. You haven't built a prototype that you have to throw away. And in particular, computational fluid dynamics can tell engineers exactly what happens inside of the engine, so that the designers can look at the different flow patterns and try to exploit all the things they learn. So I'll just try to show an example here of one of the simulations that we've been doing on high-performance computing system. This is a high-pressure turbine blade, and we can see there are some very large-scale incoming structures that we see coming into our domain here. They come from the combustor, these interact with the leading edge of this blade, and they kind of wrap around this leading edge. They get very strongly stretched. So you get these very long structures that develop over the surface then of the blade. We can see shock waves that basically are located on the blade. The flow goes from a laminar, so very smooth type pattern, to turbulence. So we have lots of smaller scales. We see acoustic waves here, so noise is produced by the edges. And we have vortex shedding, and on both sides of the blade, we have large structures that are impinging onto the surface. And one of the issues is that these structures, they actually mix the flow. So they bring some of the hot gas that comes from the combustor, and they bring that to the blade surface. And this kind of heat obviously has to go into the metal, or goes into the metal. And with the temperatures that we see here, we're running the risk of a blade starting to melt, which is, of course, something that we don't want to happen. So understanding this in detail is very important, because then we can also use this information to design appropriate cooling systems of these blades to protect them. So there's a lot of information we can gain from these simulations. And so we use high-performance computing really to do those kind of detailed simulations where we get all this insight and we get all the detail and the required accuracy to understand the physics. But of course, these simulations are very complex, and we can have up to 10 to the 16 degrees of freedom. So we have to kind of use supercomputers. If we don't, we'll wait a long time. So if we want to do one of these simulations on a notebook, it'll take us a few thousand years, which clearly is not something we can afford to do. But we can do those kind of simulations in a few weeks or sometimes months on systems like Gaudi at NCI. Nevertheless, that's still too expensive, of course, for industry to design new products. And to avoid these very high simulation costs, industry uses modeling. And I'll talk a little bit more about modeling later. But one of the ways of improving the modeling that has been kind of starting to find its application into fluid dynamics has been machine learning. And I want to talk a little bit about high performance computing's role in machine learning for fluid dynamics and modeling. One of the issues is that the modeling that has been used so far in designing engines and doing other things in computational fluid dynamics can actually be quite inaccurate for certain problems. And one of those problems is, we can find in a jet engine. So if we just look at essentially the simulation we just looked at and take a time average of that. So we then look at a slice just down in this wake region. So this is behind the blade, and we take a model prediction. So this is from a model. This is from a higher fidelity simulation, and we kind of look at the profiles along these blue lines and compare them. We can see we get a much higher peak of this so-called wake deficit, which is an indicator of how much loss this blade is producing when compared to the high fidelity solution. And this large difference obviously doesn't give us a lot of confidence as a designer to then tweak our designs, try to change things, because we don't know whether the solution we're getting from these models is actually representing the real fluid mechanics correctly. And this, of course, then limits the impact that computational fluid dynamics can have on technology development, because we have to build in safety factors, et cetera, and we can't really design optimal machines. So in this talk, I really want to talk about high fidelity data. How do we get it, and what can you learn from it? But also, how can we then use it to, in combination with machine learning, to improve those models? Okay, so let me start by talking about high performance computing for simulating what really happens inside of the engine. And a big part of that is, of course, having a code or software that can run on a large scale system, and then also is producing the correct results for the flow inside of a jet engine. So we've developed a code over many years, of the order of 15 years by now. That's been very thoroughly validated. So we can see we've done numerical simulations, compared them to experimental data, and we get very good agreement for flows inside of jet engines. So we can trust the results. It's a quite flexible code that we can do all kinds of problems with. So we can also look at noise that is generated by certain blades. We can look at flows in the corners where the blades are attached to the hub, for example. And all kinds of other problems. We can even do structures that are actually vibrating or that are flexible. So this has been a recent addition to the code that is enabled by a so-called immersed boundary technique that allows us to do movements. And that same technique even allows us to go for very complex structures. So for example, you can have a rough surface on the blade, or you can put a certain texture on and see what is the effect on the performance of the blade. Now, one of the keys, of course, is that these codes are efficient. So this code, we spend a lot of time also in collaboration with some of the supercomputing centers to optimize the code so that it runs very well on large numbers of CPUs and also GPUs. I'm showing a particular example here of a so-called scaling test on Gaudi, which is the NCI machine. And we can see that when we use 192 cores, or if we use 12,288 cores, we see a significant speed up. So it should be ideally a factor of 64 speed up. We don't really get there, but we get pretty close. And we're quite happy with those kind of performance numbers, because it simply means we can divide up our domains into many more cores, and they are all running in parallel. So the time to solution is a lot faster. And this is essentially what I mentioned earlier, that rather than waiting for years or hundreds of years or more, we can actually get answers in a few weeks' time. Okay, so this is the code. And I just want to talk about one example on how we use these high fidelity simulations to try and help designers make certain decisions on how to build a more efficient engine. And one of the big questions that always kind of occurs when you design a new engine is if you have blades that are in, for example, here, the low pressure turbine, you've got a rotating blade, you've got a stationary blade. What should be the distance, the streamwise or axial distance here between those two blades? So that's one of the design choices. Now, if we make the distance very large, that makes our machine much longer. If it makes the machine longer, we have issues with weight of the overall machine, and there are also rotor dynamics issues, etc. So you want to keep it shorter. So a small gap, intuitively at least, is better because it gives us a lighter machine. But what do the fluid dynamics tell us? What happens if we have a shorter gap? And this is what we wanted to understand. So we have run a number of simulations with different gap sizes. So essentially, on a modern low pressure turbine section that we received from one of our industrial partners, and we're running it at real engine conditions. So those are exactly the conditions that we would see in an engine that is in operation. And this is already a quite expensive simulation. So it's of the order of 10 to the 14 degrees of freedom. And we're looking at two gap sizes in particular. So 21% of the chord length of one of those blades and 43%. So let me just show you an example of what the structures, the turbulent structures, look like in one of these cases. So here we can see the blade and the next blade. So it's obviously a number of blades, and the flow has to go between or through that passage. And we can see there's a wake coming in from the previous blade. And this is kind of a previous wake that already has gone through this passage and been highly stretched. And then these wakes by themselves are producing their own wakes, of course. So if we just click through a number of snapshots here, we can see how these wakes are coming in, how they get very strongly distorted and interact with the other wake of the blade. So it's a very complex flow field. And we really need the high fidelity type simulation here to get the physics right. And I'll talk more about that when I talk about the modeling. Okay, so the difference here between the small gap and the large gap, which I've labeled SG and LG in these plots, we can see the difference between those two cases in a quantity that essentially represents the production of turbulence kinetic energy. So how much energy is contained in those turbulent structures that are going through the passage, and how much of that energy is actually being produced by the process. So this here is the small gap case, and we can see the trailing edge of the previous blade is closer to the leading edge of the next blade than in this case. So what happens here is that these wakes that are coming off this blade, they don't have a lot of time to decay before they go into this passage, while here they have a lot more time, of course, to decay because they've got a longer distance to travel. And the result of this is that there's actually a lot more production of turbulence in this passage than there is in this passage, simply because the intensity of these wakes coming in here is a lot higher. And production of turbulence, you can kind of also see as an indirect measure of eventual loss, because the turbulence that is produced will also have to decay or be dissipated. And dissipation of turbulence is pretty much an entropy generation process, which is loss. Okay, so we see an increased loss in the small gap case simply because that distance is smaller, we have much higher intensity coming in, and that high intensity turbulence has to dissipate more, producing more loss. Now, we can quantify that by looking at, again, profiles downstream of the wake, and this is a measure essentially of the loss. And what we can see here in this plot is this additional lump that basically will travel downstream here is producing an extra small kind of hump away from the main wake. So the main wake here of this blade is given by this peak, but then we have this additional lump of turbulence that is coming through, which in the small gap case gives us a larger loss contribution. And if I basically integrate this and look at the overall loss, so let's just look at the black bar here of this particular kind of mixing loss. That's a particular measure of calculating loss. And comparing between the small gap and the large gap, we can see that the small gap case has a significantly higher loss level than the large gap case. Now, what does all this mean? The conclusion really is that if we have the gap size between these two blades, it actually increases the kinetic loss by 0.25%. Now, a lot of people, of course, will say, what is 0.25%? It doesn't mean anything. But if we think back to our numbers earlier, where we have numbers like 350 billion liters of fuel are being used, every fraction of a percent is worth fighting for. And because these machines already are very mature, it really is, fighting for these last few percentage points what makes a big difference in the turbine machinery or gas turbine world. Okay, so this was one example of how can high performance computing give us insight into, what are the physical processes and how can a designer learn from this or use some of this information. Now I want to switch to how do we use this data in conjunction with machine learning. And I want to talk about a particular way of machine learning. But first of all, what does turbulence modeling look like? What does it mean? This very high cost of performing high fidelity simulations of a turbulent flow is really all down to the fact that turbulence is a multi-scale phenomenon. So we've got very large eddies and we've also got small eddies, and we've got to resolve all of these turbulent scales. So for example, in this picture that, this is a snapshot of the simulation that I showed earlier, we've got these very large eddies that are coming in, but then we've got very small structures that are sitting in these layers close to the surface or in the wake. So all of these have to be represented. And in fact, just these very small structures that are sitting very close to the blade here, we need hundreds of points across each direction here to actually represent them all faithfully if we want to resolve everything. So the solution really to reducing cost is to say, I don't want to resolve all of these structures. I actually want to model them. And essentially, I want to model their impact on the mean flow. Because at the end of the day, it's really just the mean flow or the time averaged flow that matters to a designer. we can use all that information to then basically find out what is the drag of a blade, what is the performance of a blade. And that's all we need to know if we want to build a new engine. We don't need to know every single detail. So this is the idea of turbulence modeling. We want to go from this kind of situation where we have all of these little eddies and all the details to something where we just have an averaged representation of that flow field. Now, how do we do that? We need a model that represents all of these scales of turbulence. And if we just look back at this, one of the snapshots I showed earlier, we can see it's a very complex situation, and we have different kind of scales. So there's very small eddies somewhere here. Then we have some very elongated, long vortex tubes that are sitting here that basically have originated from other scales that actually look much more homogeneous. So it's a very complicated overall flow field with lots of different scales, lots of different, types of vortices. So it's very hard to model. That's essentially what I'm trying to get at. And turbulence essentially can be seen as providing extra dissipation of energy. So it just kind of diffuses out things. And this is really kind of why people typically model the turbulent stress analogously to molecular diffusion. So the turbulent stress, which kind of is this expression here, is simply modeled as some kind of turbulence viscosity times the strain rates, so the velocity gradients. And this is just, a simple analogy to how we have molecular diffusion. Now, one of the problems with this is, and this is one of the things that goes wrong with turbulence modeling in a general case, is that this linear coupling between the strain rate and this turbulence stress, it doesn't capture any anisotropy. And as we just saw in the example I showed before, a lot of these structures are highly anisotropic, meaning that they are much longer in one direction than they are in another direction. So how can we actually represent this with such a linear model? And so this is one of the issues of turbulence modeling, and there are others, but I'll focus on this one here. Now, this Reynolds stress term is prevalent in all of the areas of the turbulence models. So both in the transport equations you have to solve, and also in the closure of the governing equation of fluid dynamics, which are the Navier-Stokes equations. So how can we improve these Reynolds stress models? And this is where hopefully we can see the connection to the machine learning in a second. Well, one way of improving these models is to just extend that linear approximation. So going from something where we just have a scalar viscosity to a situation where we are using much more information. And what we want to do here is we want to include higher order gradients. So we just take this normal model, which is used in a lot of commercial codes and by a lot of designers, and we add this red term here. And this is just a linear combination of a bunch of additional tensors. And these tensors, we call them basis functions. They are independent tensor variables. And then we have these coefficients. So we want to build some kind of nonlinear model that is a linear combination of these basis functions. But what we don't know is what are these coefficients. And these coefficients by themselves can be also functions of certain other variables, which are just independent variables as well. So with the high fidelity data, we actually try to find these zeta coefficients as functions of these independent variables I, k. Right, so how do we find this zeta that gives us the best model? And this is something we would like to do symbolically, simply for the reason that if we get a symbolic model, so an expression we can write down, that expression then is, we can interpret it, and we can also easily implement it into a CFD solver and run new simulations. So this is kind of the reason why we've chosen to not go for things like neural networks, because they hide a lot of the sophisticated modeling they can perform in the network, and you can't really interpret them as easily as you can if you have a mathematical expression. So that's one of the main reasons. And we do this by using evolutionary algorithms. So we basically want to evolve a suitable function for these coefficients. And it's pretty much a concept borrowed from biology. So it does follow the concept of survival of the fittest. And we essentially introduce incremental improvements into the models via genetic operations. And they can be cloning, mutation, crossovers, etc. And I'll explain this in a second. Now, when you have evolutionary algorithms, you don't always get expressions that are syntactically correct. So how do we do this? Because we need a model that you can write down and that is actually correct, that can be solved on a computer. And the way we do this is to use a specific kind of evolutionary algorithm, which is called gene expression programming, which transforms symbols to equations. So essentially, we have a chromosome, which is a list of symbols that exist in the code, in the machine learning code that we have to develop. That kind of chromosome has a head, which contains the function set, and then we've got a tail, which is a terminal set. And essentially, I don't want to get too much into detail here, but you can take this chromosome and you can write it as an expression tree, and these expression trees you can then basically convert into an equation. So this equation here, which is hopefully our predictive model, can be represented by essentially this chromosome. And this chromosome is what we're going to keep evolving over many generations. Okay, so how do we do this? And I've got a schematic here of this evolutionary algorithm. So we start with a random population of models. And we try to kind of just change a few things here and there. So here we've just replaced one entry, but of course we can do much more aggressive things. There's another one here, but you could also have completely different initial population candidates. For each of these models, as I showed on the previous slide, you can write it as the chromosome as an equation. So you can now take your equation and you can test your equation, meaning what does your equation predict and how good is that prediction compared to your reference data? And that comparison essentially is evaluating the fitness of the model. So is the model a good one or is it a bad one? And if we have good models, which we call fit, we keep them. And the not so good ones, they get thrown out, which is kind of our natural selection process. So after this natural selection process, we are left with the good models. And these good models then go through the process of having mutations or genetic modifications. So we can either put in mutations, we can have transpositions where we switch over certain parts of the gene to another part. And we can combine them. We can do all kinds of operations. And by putting in these modifications, we basically get new models. And these new models basically get updated into our whole pool of individual candidates, and they are basically, again, evaluated for their fitness. And we keep going in this loop until, of course, eventually we get to a certain fitness value where the models are really good, and we can stop the process and say, these last few generations of models, they are the best models that we're getting out of this process. They approximate the data the best, and they are our new models that come out of this training process. Okay, and all of this is a little bit simplified because we have to do this for tensors and for vectors in our case, because the Reynolds stress or the turbulence stress is actually a tensor quantity, but it's basically an extension of this approach to tensorial quantities that have multiple entries. Okay, so this is the overall process. Now, what does it produce and does it actually work? Okay, so I'm going to take my example here again. This is my high pressure turbine example, and it's been run at a certain speed. So imagine this is when you're flying at cruise. And this is the setting that produces a particular flow speed inside of the engine. And I'm taking the data that I've produced from one of these very expensive simulations on one of the supercomputers. Now, this is the original model that we have in common commercial codes in terms of turbulence model. if we use our machine learning technique, we basically get this extension. Okay, so these were this linear combination of the red terms that we added. And this has come now from training a model on this data set. Okay, so this is the machine learned extension. And we can see one of the key things is that it has a very large coefficient in front of the first basis function. And this basis function here is actually very similar to this term here. So we can physically interpret this. What this means is that this new model is going to provide a lot more dissipation than this original model. And we can actually see the consequence of this pretty quickly, right? So we take this new model and we try to predict the flow for a number of different turbines. So the important part here is also that we've trained it on this particular case, but we're testing this model on different cases. So this is again a high pressure turbine, but it's at a higher Reynolds number, which means that, you know, while this was maybe a cruise condition here, the pilot would accelerate, you know, throttling up the engine to a higher power setting, and therefore the flow would kind of, you know, be faster essentially in this turbine, and it's a different situation. Okay, but what we can see is that our new model, which is the red line, compares much better to the black line, which is high fidelity data, than the original model. So the original model, which is just this blue box here, is our baseline. So we see a significant improvement of our new model here. We're testing other turbine blades. These are low pressure turbines, and they are quite different. They have a different shape. They have much smaller Reynolds numbers. So, you know, they have less turbulence in a way. And again, for both of these situations, we see a significant improvement of the new model prediction versus the baseline model. In fact, the error is reduced by a factor of more than 5 for all of the cases we tested. So the new model that's been trained on just one data set performs very well on all the test cases that are at quite different conditions and also quite different geometries, which is very encouraging. Because essentially it means that, you know, we haven't overfitted for a particular case. We actually have a model that generalizes quite well to a number of other conditions. Okay, and we can also use this machine learning framework for heat flux modeling. For example, if we again look at a turbine blade, they have to be cooled so that they don't melt. And one of the cooling technologies is basically to blow cooler air out of the blade along this surface here, so that the edge, the trailing edge of the blade doesn't melt. So if we just take a look at this region here, we've simulated this region here using high fidelity simulation. Again, this is what we do on large scale computers, and we can see how, you know, the different gases from outside and the inside, they mix, and you get a kind of a turbulent flow here, a mixing flow. Now, typically heat flux models, this is the heat flux vector, also use a kind of a linear coupling to the temperature gradient, using again some kind of turbulence viscosity over a turbulence Prandtl number. We've replaced this linear expression here with a gene expression programming learned model, which is a little bit more complex than just having that constant turbulent Prandtl number. Now, what are we getting? We are looking now at the temperature along this wall here. And if we look at the high fidelity data, you can see how the high fidelity data drops pretty quickly, and we see this kind of behavior. This is a non-dimensionalized temperature. Essentially, the green solid line is a baseline calculation that uses the standard design tools. We can see that it really doesn't get this decay right at all. But if we look at the trained heat flux model that we've obtained using this machine learning approach and building it from this data that we produced, we get very close to this high fidelity data. Again, you could argue here, well, you're testing your new model on a data set that you've used for training, so there's no surprise that you're seeing improvement. Well, that's exactly why we're taking the same model here, and we're actually applying it to other cases that we've tested. These are test cases where this thickness here has been changed, and also the flow speed of the cooling jet has been changed. So they are two examples of different operating conditions. And again, the blue line here always does very well, agrees very well with the high fidelity data, while the baseline models, so the standard models, they don't do very well. So we see a huge improvement here with these machine learned models. Okay, so what is the ultimate goal with all of this? Well, ultimately we want to help design better jet engines. They are very complicated machines, so we can't run a high fidelity simulation of the whole machine to help designers improve these engines. But what we can do is we can take this, we can try to simplify it into certain building blocks. We can run simulations, as I've shown, of the high performance, high pressure turbine, looking at low pressure turbine, blade to blade interaction, looking at the flows and corners, all kinds of different scenarios. Then we can use all of this information for physical insight. So if we can understand what's going on, if we change certain things, we can exploit that. But also we can use machine learning on this data to produce better models that have higher accuracy. And with these new models that we've developed from our data, we can then help to design a better engine. Or actually, we can pass these models on to the companies, to the OEMs that actually are in the business of designing better jet engines. Okay, and that's it from my side. So thank you for your attention, and I'm open to answer questions. Before I do, I'd also like to acknowledge all my co-workers that have been an instrumental part in producing all of this nice research. So Drs. Weatherid, Pichler, Zhao, and Tagiri, and Lav, and also Fabian Baszkowski, who's currently working on our machine learning framework. And I'd also like to acknowledge some of the other computing centers that we have been running simulations on. So thank you very much.